part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the retarded potentials in fields. We're going to derive them. So the basic question is, well, we'll remember our static expressions for the electric potential, magnetic vector potential, electric field, magnetic field, and the whole thrust is how do we go over from those expressions to potential expressions and electric and magnetic field expressions that are valid for time-varying cases. So let's go back to the static case. We haven't used these expressions in quite some time. Anyway, the electrostatic potential is 1 over 4 pi epsilon naught volume integral of the volume charge density over the magnitude of the separation vector. Magnetic vector potential is v naught over 4 pi. Volume integral of the surface, or rather the current density over magnitude of the separation vector. Electric field is 1 over 4 pi epsilon naught. Volume integral over the volume charge density, separation vector over magnitude of separation vector cubed. Magnetic field is mu naught over 4 pi, volume integral once again. Current density, cross product of that with the separation vector and over the magnitude of the separation vector cubed. And remember, prime coordinates correspond to source locations and the unprimed quantities refer to observation vector or field vector. Okay? So the question of it is, well, these are static expressions, but I want to handle situations where the charge distribution or the current distribution changes in time. So how do I do that? Let's say I just say, well, I'll just replace the charge density with not only dependence on location of the charge, but also on time as well. Do the same thing for the current density. Is that okay to do that? Is life really that simple? And the short answer is no, unfortunately it is not. Because if you think about it for 1 minute, if I were to put time dependence inside my charge density and expect, well, then the potential out here is just going to depend on the same kind of integral, and the same thing for the magnetic vector potential and the electric and magnetic fields. The whole problem with that is basically you're assuming that whatever changes take place in your charge and current distributions to be felt or sensed instantaneously. So let's say I've got my charge distribution over here and I'm interested in figuring out what the potentials and fields are over at this point. And if I do that, some changes take place, well, then I'm forgetting about the amount of time it takes the information, if you will, to be transmitted from this charge distribution over the observation point. So there's going to be a time lag between when the changes take place and then when they're actually felt or observed some distance away. Okay? So let me go back to Maxwell's equations. have Gauss's law, divergence of the electric field is equal to the charge density over epsilon naught. We have the fact that the magnetic field is divergence-free. That holds in static situations and also for time-varying fields as well, and represents the fact that no magnetic monopoles have ever been observed. So I've said that many times during the course of this series. We have Faraday's law. The curl of the electric field is equal to minus the time derivative of the magnetic field. And curl of the magnetic field, we have Ampere Maxwell equation is equal to mu naught times the current density, and scrunched up over that right-hand term is the displacement current plus mu naught epsilon naught derivative of the electric field, partial derivative of the electric field with respect to time. So one of the ways that, or I should say the way we came up with this expression was making use of the fact that the electric field in static situations, the curl of it I should say, is equal to 0. And for any vector, if the curl of that vector is equal to 0, then that tells me I can write that vector as some gradient of some function. And we chose our vector to be equal to minus the gradient of some function. That function happened to be the electrostatic potential. That's in statics. But I have that term on the right-hand side, so I can no longer go this route. What is the same, though, is that the magnetic field is divergence-free. So because divergence of the magnetic field is 0, that tells me I can write the magnetic field as the curl of some vector. So this is some vector potential. What I can do now is substitute this expression back up in here in Faraday's law. But I'm going to switch the order of the partial derivative with respect to time in the curl. And now I've got curl of both sides, vectors on both sides. So let me pull this term over to the right-hand side. So we'll have the curl of E plus partial derivative of the vector potential with respect to time is equal to 0. So before in statics, we just had the curl of the electric field was equal to 0. Now we got the curl of the electric field plus this other term is equal to 0. So again, this is just another vector. What does that tell me? Well, it tells me then that this E plus partial derivative of the vector potential with respect to time is equal to the gradient of some function. And we'll say it's equal to minus gradient of V. So therefore, I can write my electric field is equal to minus gradient of a scalar potential plus the time derivative of the vector potential. And I'm not quite done yet. So since I'm done with these expressions for right now, I'm going to erase them. Plug that expression for the electric field into Gauss's law. get my first equation in terms of these time-dependent potentials, the time-dependent scalar potential and the time-dependent vector potential. You see the Laplacian of the scalar potential plus partial derivative with respect to time of the divergence in the vector potential is equal to minus the charge density over epsilon naught. So that's one equation. And it doesn't appear to be especially useful, but I need to work this through a little bit more. Okay, now I need to come up with another expression here. So let me go ahead and substitute that fact that the magnetic field can be written as a curl of the vector potential into this equation here. Into Maxwell, or Ampere-Maxwell's equation. And once again, I'm going to go ahead and substitute in for what the electric field is. So this is minus gradient of the scalar potential, and also minus partial derivative of the vector potential with respect to time. Well, using one of those vector identities here, I can replace this by gradient of the divergence of the vector potential minus Laplacian of the vector potential again, I'm switching orders of the derivative with respect to time and the gradient. Okay, so now I'm going to rewrite things a little bit, rearrange terms. And there's your second equation. I'll read it out. This is Laplacian of the vector potential minus mu naught epsilon naught. Second partial derivative with respect to time of the vector potential minus gradient operating on this quantity in parentheses mu naught epsilon naught partial derivative of the scalar potential with respect to time plus the divergence of the vector potential is equal to minus mu naught current density. So you can see these are two ugly expressions and not very convenient to work with. So I need to figure out some way of simplifying them. And to do that, I'm going to have to do what's called a gauge transformation. So let me rewrite this a little bit because I need some more room here. remembering as well that magnetic field is equal to the curl of A, and the electric field is equal to minus gradient of the scalar potential minus partial derivative of the vector potential with respect to time. So any kind of changes that have to take that I might make in either A or V cannot affect the electric and magnetic fields. So basically I can modify A and V to simplify these two expressions, but as long as I don't modify A and B. Okay? So let's say that we do modify A. We'll call it A modified. We'll now say that that's equal to the sum of the original A and some new vector. We don't know what it is yet. And likewise, I'm going to modify the scalar potential, call it V mod. V modified is equal to V plus some additional function. Again, I don't know what it is. So if I plug these new modified potentials into the expressions for the magnetic and electric fields, B and E must remain unchanged. Let me look at B first of all. So we have B is equal to the curl of A modified, but by assumption A modified is equal to the sum of our original vector potential and some other vector. Okay, so that has to be equal to B, but it also must be the case that this curl of A must equal B. So what does that tell you? So whatever this function is, this additional function that we've added to the vector potential, the curl of it has to be equal to 0. And if its curl is equal to 0, well, that tells you it has to be equal to some gradient of some function. Okay? Now, if it also must be the case, if I plug both of these expressions into the expression for the electric field, plug my modified expressions, and I still have to get back the original electric field. So this is minus curl of the original V minus, or excuse me, not curl, gradient of the original V minus gradient of beta minus partial derivative of A with respect to time minus partial derivative of alpha with respect to time. Well, what do I know here? Well, I know this term and this term together, it has to be equal to E. So what does that tell you? It tells you that the gradient of beta plus partial derivative of alpha with respect to time has to be equal to 0. Okay, so I can plug in. I know that alpha has to be the gradient of some function. So let me go ahead and plug it in here. So we'll have gradient of beta plus partial derivative of lambda with respect to time is equal to 0. And that tells me that this inside this function beta plus derivative of lambda with respect to time has to equal to some function. That doesn't depend on position, but it might depend on time. Well, basically I can absorb this into my lambda and say, well, beta is equal to minus partial derivative of lambda with respect to time. So I can make changes to A and V, but just so long as I don't change E and B. And that means that if I make one change to my vector potential A, that has to also be a corresponding change in my scalar potential V. So in other words, whenever changes take place, it's going to be gradient, A plus the gradient is some function, and V has to be altered by minus the partial derivative with respect to time of that same function, okay? So these are called gauge transformations. Well, it still isn't concrete yet because then I have to figure out how do I apply the concept of gauge transformations to these two expressions. So we'll get to that right now. Talking about two very famous transformations. Two famous gauges, Lorentz Gauge and Coulomb Gauge. Gauge, I can choose the divergence of A equals 0, which is what we did way back in magnetic statics. So in that case, my first equation looks like Poisson's equation from electrostatics. Scalar potential has the form of 1 over 4 pi epsilon naught, volume integral of the volume charge density over the separation vector. Now you might be saying, oh no, wait a second, because it does look like whatever changes occur in the charge density are reflected instantaneously in the scalar potential. But remember, your electric field is determined not just by your scalar potential, it's determined by the vector potential as well. Okay? Now I could go ahead and write this out, this second equation out, basically this fourth term on the left-hand side, which is B0. That's not going to prove all that useful to us right now, so let's move on to a more useful gauge for our purposes, the Lorentz gauge. Okay? But anyway, bear in mind that we're not violating relativity here. Whatever changes take place here in the charge and current densities will not be reflected instantaneously in your electric and magnetic fields. Okay? So let's look at the Lorentz gauge. Because I can write it over here. Lorentz gauge, we choose the divergence of A is not to be 0, but it's equal to minus mu naught epsilon naught partial derivative of the potential with respect to time. So when I do that, I substitute that into this second equation. You'll see that this term, this gradient of this term is just going to be equal to 0, because inside here it's just going to be 0. lo and behold, what we'll wind up with is an equation that is of the form of an inhomogeneous wave equation. We've got the Laplacian of the vector potential minus mu naught epsilon naught, second partial derivative with respect to time, the vector potential is equal to minus mu naught j. So wave equations are always a good form to have your equations in, so seem to be making headway. Now we just need to look at that first equation. So we've got the Laplacian of v, and if I make the substitution, that divergence of A is equal to minus mu naught epsilon naught partial derivative of v with respect to time, I will once again have an inhomogeneous wave equation. Okay? And it's useful at this point to introduce a new operator. Define it. It's called the D'Alembertian. And it's written as a squared, and that's defined to be equal to Laplacian minus mu naught epsilon naught second partial derivative with respect to time. Okay? Again, unless otherwise specified, we will be using the Lorentz gauge. Now this brings me back to the first question I posed during this lecture today, is how do you incorporate time into your potential expressions and into your field expressions? Okay? Well, let's get to that right away. I assert that the scalar potential that is dependent not only on position, of course, but also on time can be written in this form. And likewise, the vector potential can be written in this form. So notice these expressions look virtually identical to the ones that I had on the board before. However, the time in here is not just t, it's t sub r, and that refers to retarded time. Retarded time is defined as being the time minus the displacement over c. So we are taking into account the effect of the finite speed of the fields, or the rate at which information is transferred. So we're not making that cavalier assumption that information is transmitted instantaneously. Well, I've asserted that this is the case, but must it be so? Well, how do I show that? Well, if this expression, in fact, satisfies the inhomogeneous wave equation that I've got written over there on the right-hand side of the board, then, in fact, I have derived the correct expressions for the potentials. I'm just going to go through the derivation for the scalar potential. I'll leave it for you to do or not do, it's your choice, for the vector potential. But anyway, how do I begin? Well, let's take the gradient of both sides. And since the gradient operates only on unprimed quantities, I can pull that inside of the integral sign. notice here the gradient operator does in fact operate in the charge density, because even though the position or unprimed quantities don't appear explicitly, your retarded time certainly does depend on the location of the unprimed quantities, or where the unprimed quantities are. So let's do the math here. This is and I'm going to go ahead and leave off the arguments here just to save myself a little space. So this becomes gradient of rho over separation vector plus, or magnitude of separation vector plus the charge density rho times gradient of 1 over r minus r prime. Well, what's the gradient of a rho equal to? Well, that's equal to minus time derivative of rho over c, gradient of r minus r prime. Now you might be asking, what is the derivative with respect to what? Is it with respect to t sub r, or is it with respect to t? Well, as it turns out, if you take the partial derivative with respect to retarded time or partial derivative with respect to time, it's the same thing, okay? So anyway, I just need to take the gradient of this quantity, and that'll be equal to minus rho dot c separation vector over magnitude of the separation vector. So basically it's just giving you the direction. And what's gradient of 1 over r minus r prime? Well, that is equal to before we get to that, we've got magnitude separation vector in the denominator and another one from over here, so this is going to be r minus r prime squared. And here we have minus rho, because I take the gradient of 1 over the separation vector, that's going to be r minus r prime in the numerator, over r minus r prime magnitude of the separation vector cubed in the denominator. Okay, so in order to get the Laplacian, though, I need to take the divergence of both sides. Pull the minus sign out. Okay, so basically, let me write it up over here. You need one of those vector operators rules. So we got the divergence basically of the product of a scalar and some function f. So that's the same thing as scalar function times the divergence of the vector plus the vector dotted into the gradient of the function, the scalar function. So I'm going to use this to break apart both of these terms. Okay, so it's a little bit messy here, so let me read it off. Make sure I didn't leave off anything. This is minus 1 over 4 pi epsilon naught alpha. Integral sign brackets. We've got rho dot divergence of r minus r prime over r minus r prime squared plus r minus r prime all over r minus r prime squared. And this is a vector, this is a magnitude dotted into gradient of the time derivative of the charge density plus rho charge density divergence of r minus r prime over r minus r prime cubed magnitude. And then last but not least, we've got r minus r prime over r minus r prime cubed dotted into the gradient of that scalar function rho. So what can I do here? Well, first things first, you can notice this as a delta function. And this, do the math first, it's just equal to 1 over r minus r prime squared. Now I just have to worry about these two terms. Write that in here. This will be minus, and yes, I almost forgot about it, an additional factor of c in the denominator. Don't leave that off. Okay, so do you have any cancellations here? Well, over on this side, let's see. We've got rho dot over c magnitude of separation vector squared, and this term have minus rho dot over c, and I unfortunately drew my squiggly line over the plus sign, but anyway, because of this gradient here, you have an additional minus sign. So we've got r minus r prime over r minus r prime, so we've got dot product of r minus r prime, r minus r prime. It's basically separation vector squared over, and we've got separation vector cubed in the denominator and separation vector. So it's basically something of the order of separation vector squared over separation vector to the fourth. And that leaves me with r minus r prime squared. So that term will cancel with that one. And when I pull everything else out here, we'll wind up with over 4 pi epsilon naught. Do the same thing. We've got basically separation vector squared in the numerator containing the dot product of those two quantities, and separation vector cubed in the denominator, so that leaves me with just a separation vector in the denominator. And those two terms cancel out, and I've got my delta function. I'm going to integrate that over the volume. That's going to give me a rho. This first term, well, that rho dot dot over r minus r prime, well, that looks an awful lot like the second derivative with respect to time of the potential. In fact, it is. And this last term is just minus rho over epsilon naught. And remember, of course, c squared is just equal to 1 over epsilon naught mu naught. So it's a little bit jumbled up here. Unfortunately, we don't have enough room here. But you can see we've got the Laplacian here, and that is equal to 1 over c squared second derivative with respect to time of the potential and minus rho epsilon naught. So we have, in fact, regained our wave equation. And there you have it. Because this expression satisfies the wave equation, we can be rest assured that this is in fact the correct expression for the potential. And likewise, same will hold for the vector potential as well. Okay. I'll just leave that up there for a minute before we press on. Now, to calculate the electric and magnetic fields, you might think to yourself, gee, maybe we can do what we did for the scalar and vector potentials. In other words, just incorporate the dependence on the retarded time into our charge density and also to the current density. Unfortunately, life is not going to be that simple. And in fact, you will wind up with expressions that are more complicated than you might have anticipated. And by the way, these expressions for electric and magnetic fields are called Jefimenko's equations. And to calculate the electric field, I'll just use that expression I derived earlier. Electric field, time-dependent electric field is equal to minus the gradient of the potential minus the time derivative of the vector potential. And that's why I left the gradient of the potential up here, so I don't have to rewrite everything. So first term is going to be minus, basically a minus, and we've got minus signs here, so we'll have first two terms. Basically, I just move this up there, got a minus sign, cancels out with that minus sign. We're not quite done yet because we do have to take into account the time derivative of the vector potential. And that final term will be minus mu naught over 4 pi volume integral over the time derivative of J over R minus R prime. And that is your electric field, time-dependent electric field. That wasn't too bad once we already did this work over the left-hand side. Now we need to figure out what the magnetic field is going to look like. And for that, I just recall that the magnetic field can be written as curl of the vector potential. Now, just as with the charge, your current density depends on the retarded time, and hence there is a dependence in R. So I can move the curl inside because it doesn't depend on prime quantities. But the current density, however, does in fact depend on unprime quantities. So that's why, just as with the charge density and with the earlier derivations, we had to leave that inside. We're leaving J inside as well. Now, you want to recall back the vector identity. Let's say it's got the form of the curl of a cross product of a scalar and a vector quantity, and that is going to be equal to the function, scalar function, curl of the vector minus the vector and cross product of the vector and the gradient of the function, scalar function. Once again, the gradient of one of the separation vectors just equal to minus R minus R prime over magnitude separation vector R minus R prime cubed. So in the limit that we go back to the static case, our expression for the magnetic field just collapses back down to the BO Savarla. Now I need to figure out what this we'll just look at the x component of the curl of J. That's the partial derivative of the z component with respect to y, and the partial derivative of the y component with respect to z. And when we do that, taking into account this retarded time, it's going to give me a factor minus 1 over c out front times the time derivative of j sub z and that that's going to be equal to time derivative j sub z, partial derivative of that separation vector, magnitude separation vector with respect to y, minus time derivative of the y component of the current density, partial derivative of the magnitude separation vector with respect to z. So when I do all this, ultimately I'm going to wind up with write it a little bit more compactly. This is equal to 1 over c cross product, or the x component of the cross product of the time derivative of j and the gradient of magnitude of the separation vector. I can substitute that expression back over here. And there's your magnetic field. Let me just read this off. It's mu naught over 4 pi. Volume integral all over, again, time derivative of the surface current, and cross product that with r minus r prime, all over c, r minus r prime squared, plus surface current j crossed into r minus r prime over magnitude separation vector r minus r prime cubed. So again, this is a static term. When there's no more time dependence, both of these expressions will collapse to their static forms. And here we have the time, traditional time dependent terms. So this is a lot more complicated, again, than you might have anticipated, but those are Jefimenko's equations, okay? Which we will be using in an upcoming lecture.